So we discussed this and that, and nobody asked me, and I don't remember explaining it, but why is a 0 day called a 0 day?
We didn't mention it. 0 day.
So
it's something that it's a vulnerability, for example, that you use on a certain day, and it's the first time you use it.
mm-hmm.
But yeah, just mentioning it was never used, so
there is a countdown, like we have 30 days to till this, and when it happens, this is the 0 day. The day
Well, let's see this from the perspective of the vendor who made the software in which the vulnerability was found. Normally, if you do things right from an ethical side, you discover a vulnerability, you tell them about it, and they have time to prepare a patch before you go public. Whereas in the case of a 0 day, you begin to use this vulnerability and you exploit it. So you go public, giving them 0 days to prepare a patch. Basically, that's why it's called a 0 day. Do you have any questions about what we discussed today before we move on to anything else? Mm-hmm. Well, let us discuss these concepts, provide some examples, so we could really nail it down and make sure everybody knows what this is about. Automation. So the first item in the list is automation. I can imagine that I am a car thief. I know how to open the car, how to get the tape recorder out of it, the radio, and whatever other goodies I can find. Now, in a parking lot, there are 100 cars. It takes me 15 minutes to attack a car and then get out. And if I operate during 1 hour at night, when I know that the guards are patrolling the other side of the parking lot, so in an hour, I can break into how many cars?
4 or 4.
Okay, so that's 4 cars per hour. And car thieves are people. People get tired. At some point, I need a toilet break. I have to grab a sandwich because I'm a human. I have some demands. I can't work all night because productivity goes down as a function of time. You get tired. So if I can break into 4 cars in 1 hour, and let's say I can be productive for 2 hours per night, then 8 cars is how many I can break into per day. That's my profit. If I could quantify 8 cars as dollars or bitcoins. But if I use a computer, I can automate the process and rely on such a clever thing as a for loop or a while loop. And I could just sit and watch how my code is being executed and how on a day I can grab not 8 targets, but way more than 8. So that's automation. Remote action, again, in the context of stealing stuff from cars, I have to physically be there in order to get it done. This implies certain risks, such as getting caught or cutting myself if I break the glass and you make a cut, you bleed until you die. You may be caught on camera. Yeah?
You can use robots or droids to do it for you, so it's remote action.
Okay, I can rely on robots. Let's put that aside for now. What other things can go wrong if I do this in person? Well, I get caught. It was brought up. Somebody could have an alarm system. Somebody could be sleeping in the car. So as I get in, someone could tap my shoulder and say, "Are you looking for something?" And politely offer me options, what I could be looking for and where I can find it. Huh?
And you're looking for libraries.
Yeah, maybe I'm looking for a library. Maybe somebody else is trying to attack the same car. So I bump into another thief, and then we can't figure out who gets how much out of the payload. So if you have to be there in person, there are certain potential problems. But if I can do this remotely, then the risks are lower. And somebody brought up the fact that with computers I can anonymize certain things. Yes, I could. And even though computers are not the only way to make an anonymous attack, they are a tool that can make it much more simple to implement. For example, I could buy a second-hand computer from Ptichka. I can buy a prepaid SIM card from a Mold Press booth. And then I can go to a public park where StarNet gives us free Wi-Fi. And I could run an attack script and then just walk away. Assuming that there were no witnesses and no cameras, there's no way you could trace me. And in the meantime, my script could be attacking machines in Australia or as far as Vladivostok. There is nothing that prevents me from attacking something that is physically on the other side of the planet. 10 time zones away, it makes no difference. And we've discussed technique propagation. Once the method goes public, anyone can apply it. Usually when you go to security mailing lists, people don't just explain the method they used. Sometimes they include a little Perl script or a Python script with comments and explanations on how to use it. This is how a person who hasn't invested months and a lot of money into research on how to get something done, they can just run it and collect the results of somebody else's intellectual work. So these three things make computerized attacks a more serious problem than non-computerized ones. I'm not saying that anything which is not powered by a computer is by definition not a serious attack. For example, somebody could launch a grenade into this room. They won't need a computer for that, and this will be a serious problem for our physical integrity. So if it doesn't use computers, it doesn't mean it's not serious and we have no reason to take it into account. But since this is a technical university and we talk about computer security, we focus on computers. The next thing I want to discuss today are some basic techniques that are employed by computer security industry people to make their systems better. Some of these methods are not necessarily rooted in the computer industry. They were imported from somewhere else. So let's start with this one, over-engineering. Is anyone familiar with this term? Okay, someone nodded. What does it mean?
When a system is, well, has multiple functionalities implemented, even if the initial specifications were not asking for that.
Mm-hmm. Could you give us some examples?
I can't come up with a fast example.
Mm-hmm. Well, one I remember from a couple of years ago. You know what happened at Fukushima, right? Mm-hmm. So there was a tsunami that wiped off a lot of infrastructure, and there was one specific village which was not affected because the mayor of this village built a wall that had a lot of reserve. Did anyone read about it?
No.
So what they normally do is if you have a settlement, let's say you have this building and you have a lot of them, and the ocean is on this side. So you build a wall on the side where the waves usually come from, and this wall has to have a certain height, and it is built from materials that have a certain strength. And according to their regulations, these walls have to have a certain height which is standardized. So let's say it has to be n meters high. So this person insisted that they build a wall which is higher than this requirement. And this cost more money than it was originally planned. Everybody in the village would point at him saying, "You are wasting money," instead of doing something else. And for his entire life, he was ridiculed because of that. And then he died. And then a couple of years later, the tsunami hit. And this was one of the few places which was not affected because of this wall. So that's an example of over-engineering. It was supposed to withstand this much influence, but it was built to withstand this much influence. Yeah?
That's a good example of over-engineering, but there are times when over-engineering brings bad...
There are always side effects. Could you point us to a few examples?
A general example is when some project is being over-engineered and the schedule is tight and people don't really have enough time to test everything out truly. And some things might have some vulnerabilities because of that.
Well, but that's not because of over-engineering, it's because of sloppy implementation of specifications.
No, well, there might be situations when the developer, for example, over-engineers some module on his own initiative. Not because the specifications are so. And it gets to the point where he doesn't really have enough time to test it thoroughly.
Thoroughly.
Yeah, and therefore he doesn't really release really tested out product. Okay, you're right. Sometimes programmers do that. They implement features which were not asked. And those features can contain vulnerabilities or performance, or they could impose a performance penalty, etc. But specifically when we think about security, over-engineering is about preparing for, well, expecting the best, but preparing for the worst. So, for instance, if we know that the server
is supposed to be able to handle 1,000 connections per second, we will make it capable of handling 2,000 connections per second, for example. Or if we know that there will be at most 50 gigabytes of data per day produced by whatever input people gave, we will use a hard drive that can hold more than 50 gigabytes per day, etc. So the important thing is to measure and then to make some educated guesses about where this thing can go wrong and what happens when it goes wrong. Other examples of over-engineering can be taken from the construction industry. You could go to YouTube and look for a video of the Boeing company stress testing one of their wings. So you have a wing in a plane which has to do several things. First of all, the fuel is in the wing. Second, the engines are usually attached to the wing. Third, it has to withstand to certain climate conditions, such as low temperatures up in the sky, variation in the atmospherical pressure, as well as resistance to winds which bend the wing like this or like that. So according to the standards, there is a certain tolerance. So the wing should be able to, how do you call this, to bend to a certain degree, this way and that way. And let's say that this alpha is equal to x degrees. And in this video, you can see how they stress test the load on the wing in a controlled environment by bending it slowly, slowly, until it reaches alpha. And then at some point, it goes even further to alpha plus delta. And only then it breaks. So that's another example of over-engineering. I would feel much more comfortable flying on a plane that was over-engineered than on a plane that was not over-engineered, for obvious reasons. Another trick is compartmentalization. Even though it has the word mental in it, it has nothing to do with psychic powers. But what is it about, in your opinion? This either means you have no opinion, or you are hiding the information from me.
Everybody has an opinion. Like
Yeah, so we know you have opinions. So, what is compartmentalization?
Dividing the tasks.
Dividing the tasks. Mm-hmm.
Compartment, like someone is responsible for the wings, someone is responsible for engines, someone is responsible for...
I see. Who watched the film Alien?
Which one?
It's written usually like that. Not aliens, but alien. When they were on a planet, which was converted into a prison. Remember?
Yeah.
So who saw this? So I could... So only 2 people watched this film, therefore it's not a good example. Well, I strongly recommend you to watch this film. I'm not promising I will include it in the exam, but it will help you in life because you will learn how this can help you. So there was this creature, a xenomorph, an alien life form, which has pleasure in attacking humans. And they were a bunch of people, prisoners, in a prison that was really, really huge. And this whole system, let's imagine that this is the schematic diagram of that prison. It was divided into tunnels, which had gates that would lock and isolate these compartments. So what happened is that there were tunnels in different sections, and people were all over the place, and the alien was moving around and, you know, eating and taking a bite out of whoever it pleased. And if I recall correctly, because this was a long time ago, they eventually managed to, well, I'm not going to spoil the film for you, but they wanted to steer the alien into a special section in this place. So they did this by locking out different gates, leaving it no possibility to go outside of this section. So it was trapped in here. Then they opened the section here, so the thing could walk only that way. And this is where they built a trap for it, so in the long run, the arch nemesis was eliminated. Now, where does this thing come into play? You can have this, and it's very difficult to control, because if I am here, I can move into any direction as I please, and you cannot contain the damage or the aggressor. Moreover, you cannot hide from the aggressor. If, for example, I knew there was a compartment here which I could lock, I could hide in this place, and then I don't care what happens next, because I'm safe. Another example of compartmentalization can be taken from the design of ships. If you look at a diagram of a hull of a ship, usually it is divided into a number of sections, and according to the design specifications, the ship shall not sink if, okay, let's say that we have 1, 2, 3, 4 sections. It will still stay afloat if 2 of them are completely flooded. So the point is that if someone hit this thing with a torpedo, so there's a hole here, or let's say the hole is right here in the middle. So 2 sections are now damaged, and they begin to take water at high speeds in large volumes. But if the seamen manage to get on this side and lock this section out, they are still not going to go down. So that's another example of compartmentalization. Basically, you break this system down into components which are independent and isolated, such that if one or several of them are compromised, you still have full control of the remaining parts of the system, and this cannot be breached. So you can concentrate on what's left while this is already gone. Is it clear? Does it make sense? How would you do that in a computerized system? Let's transpose those examples into software engineering.
Making a distributed system that consists of several components, and if someone goes down, the remaining system will still work.
Mm-hmm. Okay. So you distribute the system by having multiple servers in different locations.
Mm-hmm. And they interact between each other.
Okay. What if we are on a single computer? There are no other machines involved, just one system. is there room for compartmentalization within one server?
Virtual boxes. Security layers. Have many different security layers.
Okay. Wait a second. So I will write it down, because security in depth is another trick, but let's discuss it when we're done with this. So virtual machines. If one virtual machine is affected, it doesn't do anything to the other systems. How is this thing you just mentioned different from a sandbox? A sandbox is an isolated environment where you can do whatever you want, and it won't affect what's outside the sandbox. So are sandboxes and compartmentalization the same thing?
Not really.
In my opinion, sandboxes are quite limited. While when you use full-featured VMs or whatever, they allow you the same exact features. The only security moment is that if something goes down inside a VM, you have to just reinstall it, rebuild it, say it like that. Sandboxes protect you through means of limiting some functionalities. While, well, the functionalities that might have a threat to the system. While when you have different nodes that work fully featured, the only security you have is that you can throw it away and rebuild it quite fast. With a low price, that's the whole reasoning.
Okay. In this context, since you mentioned virtual machines, you might be interested in looking up this red pill. It's a small it's an exploit. Well, first of all, it's a paper published by a security researcher where they discuss and devise a method of detecting if a piece of code is running inside a virtual machine or on a physical real machine. And the thing they need this for is that sometimes when you're dealing with some unknown program, you are careful and you first run it in a virtual machine to observe what happens. Does it write something to the registry? Does it open up a port and listen for incoming connections, etc.? And if it doesn't do that and it looks fine, then you say, okay, I trust this program, so now you run it on the real machine. So what this thing does is it detects the fact that it's in a virtual machine and it doesn't do any of its nasty things, so it passes the test. But when you run it on a physical machine, only then it begins to set up keyloggers and do this and that. So there is this. You look for red pill virtual machine, and you will find the name of a researcher, Joanna Rutkowska, or Rutkovskaya, I don't remember exactly. So she is the author of the paper and the tool. So look it up and learn something interesting. Well, let's go to security in depth. What is it about? Perhaps you could make some analogies or give us some examples? Julian.
One example might be the contest from last year for reaching the next security layer. You have to break the simple one. It's complex. But there was just one type of security password.
Yeah.
For security in depth, it may be different.
sometimes people refer to this as security is like an onion with multiple layers. You peel off one layer, but then there's another one, and there's another one underneath, etc. So, the book, the film.
Yeah, there's about this, how they have discovered all of this. They have a lot of questions to answer and have to get
Well, I've read it a long time ago, so I really don't remember anything. So unless you elaborate on this. Yeah, give us more details.
It's mentioned about security and that they were trying to find out the answer, but in order to find it, they have a lot of tasks to do, and actually they should do one and get one answer, and that's a piece of code of puzzle.
Okay, so they had to hop from one point to another to solve the big puzzle and build the big picture. Well, okay, do you have other guesses on what this is about?
City Quest?
Well, Dan Brown is the City Quest. Yaroslav, what do you think? What do they say on the computer?
About City Quest?
About security in depth.
I didn't Google it yet.
Well,
should I?
What about the transporting data between two computers? And for example, there are different layers, like transport layer, network layer, application layer. On some layers, or almost on every layer, there is a checker. It checks if the code the data you get is correct one. So you have also with the key and I don't know, the key, and you check if the data is the correct one. On the different layers, it's different implementation. So you have to pass the transport layer, then the application layer.
Got it. Now let me tell you my version. So in a system that doesn't rely on this principle, you have just one layer of security. And if this layer is breached, then the whole system is compromised. When security in depth is applied, you have multiple independent layers that ideally use completely different techniques of defense. Now let's imagine a few examples. If we lived in the times of Stefan Chalmari, and we had to, it could be one of your layers. Just like I said, in the times of Stefan Chalmari, they were using VPNs to secure the communications from the Turks and the Tatars. It's well documented, and it's a well-known fact. So you have a castle. Around the castle, you have a moat. It's some body of water. Ideally, it has crocodiles. And the water turns into lava as soon as anything except a crocodile touches it. And there is this bridge. It's controlled by some mechanism, so you can enable and disable it. On the walls you have archers who can hit you with an arrow from a very far distance. So the range extends up to this point. Did anyone watch Samurai Jack? Do you know the episode, The Three Blind Archers? Congratulations. You get a bonus point for the exam. All of you have to watch this episode. So there were three very extremely qualified archers who were blind, but who could still hit you from a very far distance with great accuracy. So those archers were employed by Stefan Chelmade to defend castles. Now, even if you got past the bridge and the crocodiles, you still have to break the wall somehow, because you can't get in through this way because the walls are really, really thick. And here they have a gate made from the hardest wood you could possibly imagine. And even if you got close, besides the archers, there are people who can throw boiling hot tar at you, acid. What else do they use these days? Ecstasy, LSD, all of those things that are thrown at you to confuse the enemy, etc. Now, let's imagine that we are the bad guys attacking this thing. The first layer of defense, oh, I forgot about the landmine field. So you have to first get through the landmines. Let's say hypothetically somehow you did it. But then, well, and you did it because you found a mechanism that can hover. You used the quadcopter to fly above the surface. So you got past this layer of defense. But another layer of defense uses a completely different technology. The archers use the sense of sound to hear your steps. How can you get past the archers?
With some shields?
Shields, maybe. With a tank, maybe. And even though the tank will get you past the range where the archers can hit you, you will not get through the moat, which turns into lava as soon as anything touches it. And the crocodiles will be there waiting for you. So the point is that just like in an onion, there are multiple layers. And in this case, you have multiple layers of security. If you compromised one layer, and if you manage to get past another layer, there are still plenty of other layers to go through. That's why a system that has only one layer is very vulnerable, because a single successful attack can bring it down to the knees. But if a system has multiple layers of defense, then you have to really, really plan your attack. This requires intellect, this requires planning skills, more resources, and sometimes there is a time window which can be very narrow when things can be performed. For example, when one of the archers goes to have a lunch break, then you have a 33% less likelihood of being hit by an arrow. So that's security in depth. How would we transpose this concept to computers? And to give you more context, remember this machine here, which we had drawn on the previous class, the computer with the secret recipe for cookies? It had a CD-ROM, a floppy drive, an internet connection, blah, blah, blah. How can we secure it at different layers? What can we apply?
As Alex already mentioned, you can use different security tricks at every, let's suppose, high layer.
Mm-hmm.
So at the session layer, we apply some techniques, application layer other techniques, and after that you encrypt data.
Okay, so up to this point, you gave me examples of securing the network side of the attack tree. What about attacks against, what about social engineering attacks? How can you protect that data from a social engineer?
Identifying your friends on Facebook. For example, if somebody breaks my password, then he'll gives me 3 pictures of my friends and tells me, do you know what are their names? And if you answer correctly for these 3 pictures, then you are allowed. So it's something you cannot automate, or I don't know.
Well, you can automate by randomly giving some names. What if it works?
Yeah, so it's a way to defend against social engineering.
Remember the password security challenge that he brought up? One of the levels gave you a hint saying that the password is the name of your teacher's friend. Did anyone pass that level? Okay, Georgi Pantas. He is the person who gave me the server where I deployed it. How did you find this name?
On Facebook.
Yeah, so my list of friends is public.
Yes.
Well, it was done on purpose. So you could actually solve this problem. I didn't. What about that system, hypothetical system that we discussed previously? We brought up the possibility of taking the hard drive out. How do I prevent that? By putting the case in a box which is not physically available. Yeah, we can do that. How do you prevent me from stealing the box entirely?
You can buy special box in a bigger box.
In a bigger box. And its box is all the way up and all the way down.
You can store the data in a cloud or use just a thin plan
to access something somewhere else.
In a data center with lots of hardware.
Now, as for the CD-ROM, I could perhaps go to BIOS and say boot from a CD, boot from a compact disk that gives me a password reset feature for Windows. So I could set the password to whatever password I want, then boot normally, and copy the file. So a layer of security against that would be to password protect the BIOS, to disable booting from anything except the built-in hard drive. Sometimes certain system administrators or security staff, they use silicon or some other amorphous material to cover the USB ports to prevent people from physically connecting something into the USB port. So that's another method of defense you can use. So you can go on, and that is what security in depth is about. If you don't use that, you risk failing to secure your target if one single attack is successful. And I would also like to bring another example, which is the concept of a monoculture. Which is a culture so homogeneous that a single threat can wipe it off. And an example would be, well, it's not a perfect example, but it's better than nothing. When European explorers and colonists went to the Americas, a lot of the locals died. Do you know why?
Because people have different diseases, and in Europe they were having antibodies against this disease, but when they went in USA, the people there didn't have this antibody.
Yeah. So one reason is because they brought swords and other weaponry, and they really killed them. Another thing is that Europeans had an immune system which was optimized for one set of enemies, whereas the people populating those other regions had immune systems that were not prepared against these new threats. And when the Europeans came, a lot of Native Americans succumbed to diseases and died because of smallpox, which was one thing that killed them. Syphilis was another. Yeah.
Another thing that they just drove off the natives, and they were forced to flee some places. It's not so
user-friendly.
User-friendly.
Yeah. So in this example that I brought up, it's mono in terms of immune system development. If there is no variety in a population, then this entire population can be the victim of some virus which they have no idea how to deal with. So that's why diversity and interbreeding is usually a good thing for an immune system. And this is one of the layers a society can use to increase their chance of perpetuating the species and not vanishing. Do you have any questions? Well?
Sorry to bring it up again, but I kind of didn't understand why is the
Compartmentalization?
Compartmentalization. How does it work? Well, yeah, we have sandbox, but how do we apply it on just a single program?
So when you build this program, it could be a monolithic thing that does everything. Or it could be divided into components. For example, this is the database. This is the core that implements the logic. This is the web interface, etc. Somebody may have found a way to compromise the web interface in such a way that it's not available. But the database is still intact. Its integrity and its confidentiality were not breached. So that's one thing. Let me come up with another example. In certain countries, there are regulations that make it imperative for you to store personal data in a separate database that is not related to the other database. For example, let's say we have a database of personal data where you have things such as the first name of a person, last name, date of birth, place of birth, and a few other things, and the social security number. And all of them are indexed by some unique integer. It could be IDNP, IDN, or if you listen to Kino, it could be порядковый номер на рукаве. It doesn't matter. It's some number. And in this other database, you have the same number, which is correlated this way, associated with other stuff related to this user. For example, my what do they have? My list of friends, my musical preferences, whatever. Huh?
Favorite color.
Favorite color, yeah. So if someone managed to somehow find a vulnerability in the web interface, let's say it's an SQL injection, and they managed to get me to insert some stuff in this database, but this one, because it's physically kept somewhere else, was not compromised. Or let's take a different form of attack. Somebody raided our offices or the data center where this database is kept. So they just unplugged the machines, took them out of the racks and went to the, I don't know, they just took off. So now they have this, but they don't have this because it's physically located in a different place. And you should know about this site. datipersonale.md. As far as I know, we nowadays have some legislation in Moldova where anyone who deals with personal data, and they give you a definition of what it is that makes data personal. Anyone who deals with personal data must comply with certain regulations. And in Germany, for example, the rule says that personal data must be stored on a server which is geographically in Germany. Even if the rest of the infrastructure is in Amazon's cloud in the US or somewhere in Droslichain, the personal data must be physically in Germany. So that's one other aspect in which compartmentalization plays a role. If that's compromised, but the other parts of the system that are here remain intact and continue to be safe. Another technique is security reuse, which stands for reusing methods that were used in the past. What are the drawbacks and advantages of this approach?
Well, if we're using methods used in the past, that means if there are some vulnerabilities in those methods back then we're just dragging them along until now. So we just keep propagating the vulnerabilities for the systems.
Okay, so on one hand, it's bad news because if a system has, if a security mechanism has some vulnerabilities and we keep reusing it, we are vulnerable, therefore insecure, therefore the system fails to accomplish its objective. What about advantages?
If we will reuse the good parts, maybe it will help us to develop new good systems.
Okay, so if there is something that is known to be reliable, which has withstood the test of time, why not use it? Why reinvent the wheel if we already have a wheel and it works? So the good news is that if something works and is confirmed and is tested by time, there is no reason not to reuse it as is. And the risk is if you are using something that used to be effective in the past, it doesn't necessarily imply that it's still effective today. For example, let's go back to the 3 blind archers defending this castle. Somebody said, well, you could use a shield to cover yourself from the arrows. But what if the arrows, and let's say that in the past this was enough, you could protect yourself, but now the arrows are loaded with a small explosive charge that detonates as soon as it contacts a shield. Well, the shield works against the old methods, but it's not working against the new methods. It's not going to help you from being hit by a bullet, by a laser, or by a spinning razor blade that flies your way. So security reuse is something you need to be cautious about. Security through obscurity is another trick you can keep up your sleeve. if you are wearing a shirt. We've discussed this in the previous semester in the course about computer networks, I think. Therefore, I will ask one of you to summarize it in a few words.
This means that enemy knows how the system works, but doesn't know the key or the password, something that's secret or personal. Who manages the system.
Any other opinions?
If it's for obscurity, that means the information about how your security system works is hidden from the general public.
Yeah, so what does obscure mean?
Something unknown.
Something unknown, hidden, just like in Romanian, obscur. For example, un poet poate să moară în obscuritate. Nobody read their poems. In the context of computer security, you can hide certain details about the internals of your system. For example, let's say I am running an SSH server to connect remotely and manage my system. Normally, SSH uses port 22, but I can make it work on port 45. So whoever tries an SSH client and connects to port 22 will get a connection refused or connection timed out, and they will say, damn, I can't use any SSH exploits against this system. Or I may even not tell you that I'm using SSH to remotely manage my system. And then it will be up to you to figure out what is it that I'm using, if I'm using anything at all. I might be using Telnet, not a good idea, but still. I might be using TeamViewer, VNC, RDP, NX. There are a lot of other ways you could do that. But as long as I'm not telling you which one I am using, you don't know how to begin, how to build your attack tree. Because this information is not available. Do you expect this to be a barrier against a person who really wants to kick our ass?
No.
Why not?
Well, because through different kinds of attacks, he's still going to get some info out of it. So he's going to get, one of the attacks is going to be denied, the other is going to be denied, but they could be denied in different ways. So in the end, he's still going to get a general picture of what's behind your security. So your security is simply based on the fact that nobody knows you're using SSH on that port, and that's your only protection. It's just going to take a while until somebody figures out.
Exactly. So the point is that if you use just security through obscurity and nothing else, it might protect you against script kiddies or first-year students or even graduates from ASEM, ULIM, and USEMIA. But it's not going to protect you against people from this group, for example. It's perfectly normal if you use this as one of your many layers in a big system. But if security through obscurity is the only thing you rely on, you will most likely suffer because of this decision. It's not a good choice, not a good thing to do. And this brings me to another thing, Kerchoffs' law, which is a very big deal and a really important, crucial concept in security. He was a person in the French army who thought about security. You know, he liked to think about security, And you know that in the army, they sometimes have to transmit messages about locations of troops, how much food they have, how many bullets there are left, which way the tanks will be coming from, etc. And it is very important that the enemy doesn't get their hands on this information, because if they do, your attack can be compromised, they can ambush you, they will learn where your weakest link is, etc. Therefore, they figured it would be a good idea to somehow transform the messages such that the enemy can't read them. And this is where the keyword encryption comes into play. And there are different encryption algorithms, the purpose of which is to take some piece of information along with some secret key. You combine them together using a special method or an algorithm, and at the output you obtain a cryptogram, or just a crypto, which is an enciphered text which cannot be read unless you know the key. And he stated that for a system to be secure, it is important that the following condition is satisfied. It is truly secure only if the enemy knows absolutely every single thing about this system except the secret element. In other words, it's not a problem if you know which encryption algorithm I'm using, what the frequency of each message, I mean, how frequently we exchange messages, how long the messages are, etc. But as long as the key with which we encrypt the messages remains secret, the system is still secure. And this normally applies to encryption algorithms or cryptography in general, but you could extend this law to other aspects of security. So when it comes to which port number I use, which protocol I use, even if all of this information is public, I can still be secure if I'm using, well, if the secret data are kept secret, and if I'm using technologies that were not compromised. For example, SSH uses encryption, whereas Telnet sends stuff in plain text. So if I authenticate to a remote system using Telnet and someone sniffed this network traffic, they will see my password. So remember that you could see this as the antagonist of security through obscurity. In an ideal world, you continue to be secure even if everything about your inner workings is known, except the secrets or the passwords. Of course, this doesn't mean that we shouldn't give the enemy a hard time and not reveal information about our system. The point is that even if this information becomes public, we still maintain our level of security. Do you see this point? It's really important that you understand this. Does it make sense? You have a question?
Maybe not a suggestion, but I know that when they were choosing the newest SSH encryption algorithm, they were saying it should be, this algorithm should be known, but for everybody, but it should work. So they encourage the information, to give the information about the algorithm to other people. So they can test it and find, the community can find the bugs. easily.
Well, that's exactly the point of Kerchoffs' law, that when you roll out some new encryption algorithm, you can't trust it unless people have examined it. They looked at it with a critical eye. They tried to look for loopholes, weak spots, and only if this algorithm or system passed the scrutiny of qualified brains looking at it, only then you can say, well, it makes sense to use it. Another important concept is that of securing the weakest link. The point is that if you have a system, let's represent those security mechanisms as elements in a chain. And I can take this chain and I can begin to try to pull it apart. At some point, it will fail. Where will it fail?
At the weakest link.
At the weakest link. So if, let's say, if this one is sloppy, it will break easily. Therefore, the security of the entire system is now compromised. Well, not if you use security in depth. It's not yet compromised, but the enemy is already one step closer. And obviously, when you build an attack tree, as we began to work on in the previous class, besides just enumerating a list of all possible branches in which you could conduct an attack, for each branch, you could also quantify the effort or the cost, which could be expressed in terms of time, dollars, or how many pages you have to read before you understand how to use a certain mechanism. So in a tree, it is reasonable to take the path of least resistance. Let's say it's this one. And you know that how? By thinking about each of these links and assigning a cost. Let's say this is 1, 1, 2, 1, 2. And this is 4, this is 6, this is 4, and this is 5, etc. Any rational and lazy person, and an attacker can be a person, will take the path that takes the least amount of effort, time, money, and other resources. So obviously, you can spend countless of bitcoins to secure this part and maybe this one, but the attacker will not go there or here where the wall is the thickest. They will find the weakest link and attack that specific link. If you saw the film Kingdom of Heaven, did anyone watch it? Well, what they did in that film is I think they took some internal intelligence from people beyond the walls of a fortress that had to be attacked, and they learned that in the wall of this castle there was one section which was weaker than the other ones, because this is the place where there used to be a gate. Then the gate was removed, and they just put some stones there to make the wall one big thing. And this thing was not as reliable as the walls around it. So that's where they began to throw their rocks with catapults. Not here, but obviously here. So another reason to build attack trees is because by computing the complexity and the costs for implementing each approach, you obviously see what's the weakest link in your system, so you know which parts need to be strengthened such that the system is secure as a whole. Is it time for a break?
Yes.
Well, then that's it.